Here is a rather odd-looking thing. Here is me, but here is a blank sheet of paper on which I'm going to write. So what I'm going to do is I'm going to talk us through the theory behind what we're doing inference-wise this week. We're going to look at one sample T and two sample T. And before we get to those in R, I thought I would remind you of the theory behind these and maybe introduce you to a bit of theory that you don't know. So let's suppose we have some observations. x1 up to xn. Let's suppose that they're all normal with some mean and some variance, and let's suppose they're also independent of each other, which is going to be important in a minute. Now, the normality is an assumption, and one of the reasons for normality is that we can then do something with this algebraically speaking. In particular, we can look at the sample mean. And so there are some things we know about this. Regardless of the distribution of the x's, we know that the average, the mean of x bar is the same as the mean of the observations. Also, regardless of the normality, the variance of x bar is sigma squared over n. And this is where the independence comes in, because if you don't have independence, you don't have this nice result for the variance because it has covariances in it. And if the x's are normal, which is what we assumed, then x bar is normal as well. And that's what makes this work, because x bar is a linear combination of the x's. So if the x's are normal, it's normal. And so what that tells us is, if you look at this thing which we'll call z, if you standardize x bar, this thing is going to be standard normal. And if you happen to be in the position of knowing sigma squared, if you happen to be in that happy position, then we are done. Because we know the distribution of this thing, and therefore we can test our hypothesis mu equals something, or we can make a confidence interval for mu given that sigma is known. And the theory behind that is straightforward, and it all involves the normal distribution. But, this is a big but, if sigma squared not known, what are we going to do? What we're going to do is make ourselves a bit more space. We're going to estimate it by the sample variance, which is itself a random variable, so it's a capital S, which is so xi, capital Xi, minus x bar squared over n minus 1. So that's what you're going to estimate by, and then you're going to look at this thing which we'll call T, and you actually know what distribution this has, but we haven't proved it yet. So you look at this. And the question is, what distribution does that have? It isn't normal anymore because of this S on the bottom. X bar varies from sample to sample. S varies from sample to sample. There's two random variables in here, and so the distribution of T is not something that's easily known, and we have to work out what it is. So let's grab ourselves a new page, and then we'll see where we can go with this. So we're going to need some facts. We're going to need some definitions. So let's imagine we have, we'll say there's k of these guys. Imagine we got some more standard normals. Then the distribution of the sum, I need an eraser now. Let's get myself an eraser and erase that k, because I don't need k. I need j or something like that. Let's get my pen back. Alright, where are we? Here we are. So j equals 1 to k. That thing squared, that thing is said to have a chi-squared distribution with k degrees of freedom. That's the definition. So whether you want to put something lines this is defined to be distributed as that. That's a fact. This is a definition. So we can make it a fact. So we've got another definition. Let me see if I can remember what I wrote down here. Suppose you have one standard normal, which we'll call Z. Let's suppose we'll have U, which has a chi-squared distribution with some number of degrees of freedom, we'll call that K. Then, by definition, Z over square root of U over K, that has a T distribution with K degrees of freedom, and that too is a definition. So we defined two things. We defined the chi-square distribution, and we defined the T distribution. So now what we're going to do is we're going to have one more fact which comes in at this point. Comes in over here. This is a fact. If you work out n minus 1 s squared, this is the same s squared that we had before, over sigma squared, from the same normal distribution. So if you take the x's that we had before, and you work out s squared, sample variance, and you know what sigma squared is, then this thing has a chi-square distribution with n minus 1 degrees of freedom. So that's a fact. So those three facts are going to help us work out what distribution capital T has. So let's see if we can do that. How much space? I have a bit of room. Okay, so we'll write down what T is. X bar minus mu over S over root n. I have to keep remembering to call that capital S because that's a random variable. And now, what we can do is to say if we had a sigma down here, we would know what to do. So what we're going to do is we're going to divide top and bottom by sigma over root n. And if we divide top and bottom by that, divided by sigma over root n, then we haven't done anything to this ratio. And I seem to be missing. That's a divide. It's a divide. Okay. Now, this thing on the top here, this is just what we were calling Z. It's a standard normal because this has got the real sigma in it. But this thing on the bottom, what is that? Well, we'll see if we can simplify it. The root n's go away. This is S over sigma. Or if you want to write it this way, you could write it as the square root of S squared over sigma squared inside a square root. And then, I'm going to go to my notes here. The root ends have gone away, but if you stick an appropriate n minus 1 in the right places, let's put a square root. N minus 1 s squared over sigma squared times a 1 over n minus 1. Now I do need some, no, I don't, I have a bit more room. Okay, and so this first thing is something that has a chi-squared distribution with n minus 1 degrees of freedom. So we'll call that U like we did before. And that's divided by n minus 1, which is its degrees of freedom. So this thing we now know has a T distribution with n minus 1 degrees of freedom. That's how we know that the t-test, the t-confidence interval, is the right thing to use in the one sample case if we're estimating a standard deviation. That's how we know that fact. So this is all fine and wonderful. For the one sample case is now done. There is a problem, however. Let's go right back to the beginning, which is the assumption that we made here. Alright, let's have a change of color. Let's make this purple, and the assumption that we made right here. Alright, I'll go back to black now. Purple is a bit vibrant. That assumption that we made, that the x's had a normal distribution. If they don't, all of this falls to pieces. None of this is any good, except except that this thing, if n is large, this thing that I called z, if n is large, this thing has approximately a standard normal distribution regardless of the distribution of the x's. That's the central limit theorem. And also, we have a second thing, which is to say that if n is large, then either you can say t is approximately normal, or you can rationalize it by saying if n is large, then s squared is going to be close to sigma squared, because they converge in probability. And therefore, this is going to be close to z, and therefore it's going to be close to normal 0, 1. So I got to write all that down. Let me go down to the end. I need another new page. All right, give me page. And I'll have a new page at the end. Thank you. Here is the thing. If the xi are not normal, this fails. But if n is large, the sample size is large, we have the central limit theorem and approximate normality of z. Let's get it in over here. Hence, s squared and sigma squared are about the same, implies approximate, running out of space again, approximate normality of t as well, because a t with a large degrees of freedom is normal. So, that's our get-out clause. That there is our get-out clause, and I'm in the wrong place. Let me grab myself and move myself out of the way. This is our get-out clause. This is the only get-out clause we have. If the x's are not normal but the sample size is large, then we escape. The central limit theorem lets us escape. If n is not large and the x's are not normal, we are screwed. We don't know what's going to happen. And later on we're going to learn some ways around that. But at the moment we don't know what to do about that. But the consideration about normality is in conjunction with the sample size. If your sample size is bigger, then the normality matters less because you have the central limit theorem. If the sample size is not big, the normality is important. If you don't have it, you're in trouble. So that's the one sample case. So let me just make, if n not large, then we don't know what happens. Alright, so that's the one sample case. So let's think about two samples. So I need some notation for this. Let me just write down the notation I had on my crib sheet. Okay, so let's suppose we have the first sample, we'll call them x, and they are, n1, and they are normal mu1 sigma 1 squared. We have a second sample called y1 up to yn2. These can be different sample sizes, and those are normal mu2 and sigma 2 squared. So we're assuming nothing here apart from the fact that these are normal. They could have different means and they could have different variances. So let's think about some stuff that we can do. We know there's business about the x bar. We know that this has mean mu1, and the variance of x bar is sigma 1 squared over n1, getting all the subscripts right. And then we can say the same thing for y. And I didn't call these x1 and x2 because then we would have been overrun by subscripts and it would have been hard to keep them straight. So the average of the y's has variance sigma 2 squared over n2. Alright, so that we've got. And then we can look at the difference, x bar minus y bar. And you can work out its mean, and you can work out its variance, so we'll do that. The mean of the difference is the difference of the means. And again, I forgot to say all of these are independent of each other, and the x's are independent of the y's. And then the variance of the difference, because they're independent, because I just managed to assume that, is the sum of the variances. Sigma 2 squared over n2. Alright, so what do? You do the same thing as we had before. I got a bit of space here, alright, good. Move me up. Move me up, please. Alright, I am at the bottom of the page, so I'm going to get a new page. New page again. Okay. So we're going to do the typical thing, which is that we're going to standardize x minus y. We'll call this one z as well, because it is z. Is x bar minus y bar minus its mean divided by its standard deviation, which is that thing at the top there. n1 plus sigma 2 squared over n2. So that thing is going to be standard normal. And that's fine and wonderful as long as we know both sigmas. If we don't know both sigmas, we are in trouble. And the first step is to say if the sigma I squareds are unknown, then estimate them by SI squared, the sample variance of that sample. And then you end up with a thing which I guess we can call T, but we don't know what distribution it has yet, where all the sigmas are replaced by nice big square root S1 squared over N1. I don't have quite enough space. Plus S2 squared over N2. Alright, so that thing, what distribution does that have? We don't know. We don't know what distribution that has because it's got random variables in it all over the place. X bar and Y bar will vary from one sample to the next. S1 squared and S2 squared will also vary from one sample to the next. And that has a distribution that we don't know. Alright, so what we're going to do, in the hope of making some progress here, is we're going to assume that sigma 1 squared and sigma 2 squared are the same. Now, this may or may not be actually true, but we're going to make that assumption. And then, and we'll call that common variance sigma squared. And then what we've got is the same old rubbish on the top. And on the bottom, need a big square root, a bigger square root than I had before. Yeah, they're bigger square root. I actually didn't mean to do all this. We're going to do some more stuff here. Stick some brackets around there. And we'll divide by... I didn't do it this way. Let me see what I can do. This is on my page 3, which I have now lost. Okay. Okay. So I'm going to erase some of this because I didn't actually do it this way. I argued it a different way, which I'll argue now. And we're going to erase all of this. Go away. I need a bigger eraser. Alright, something like that. Okay, go back to our pen. Now, we'll think about the thing on the bottom. Then, we're going to think about n1 minus 1 as squared, as 1 squared, over sigma 1 squared, which is actually sigma squared. So I've got to erase that too. Go back to my eraser and erase that 1 there. Plus n2 minus 1 s2 squared over sigma squared. What distribution does that have? Well, this is chi-squared n minus 1 because that's what it looks like. This is chi-squared n2 minus 1 because it's got the same sigma squared on the bottom. So this is going to be chi-squared at the degrees of freedom up n1 plus n2 minus 2. And so therefore T is going to have a T distribution with that same degrees of freedom. Alright, there we go. We rescued ourselves. So if you can assume, or if you want to assume, that the two populations have the same variance, then this still works. You still get a T distribution. This is called, need more room. This is called pooled T. This is the one you proved in B57, I should think. So if you're willing to assume the two populations have the same variance, then you can make it work. Now, we made that assumption. It may or may not be true. So how about if we don't make that assumption? Then we've got to think about, where are my notes here? We've got to think about what is the distribution of that thing s1 squared over n1 plus s2 squared over n2. And if we try and do something like this, it's not going to work out. So what we do is we do something different. Now I'm going to do a little bit of pre-work just to get this organized. And for that I'm going to need another page. Page, new page at end. So let's imagine that we've got one of these samples, doesn't matter which one, ni minus 1 si squared over sigma squared. And that's sigma I squared. And that's going to have a chi-squared distribution with ni minus 1 3 degrees of freedom. And so the mean of this thing is going to be degrees of freedom, and the variance of it is going to be twice its degrees of freedom. So, see if we can make use of that. And where that goes, I'll just shortcut this because you don't need to see the whole thing, is that the sample variance is an unbiased estimate of the population variance, which is not terribly surprising. Let me just write down the step I missed. Is ni minus 1 and variance is twice that, because the variance of a chi-squared is twice its degrees of freedom. Alright, so that's what we've got so far. This is this, and the variance of si squared works out to be 2 sigma I to the 4th over n minus 1, ni minus 1. Alright, so we've got those two things. So now what we can do is we can say, let's go back to this denominator. Let's go back to this thing and try and work out its mean of variance. So let's work out the mean of s1 squared over n1 plus s2 squared over n2. And that we can do because we got the ingredients here. The mean of a sum is the sum of the means, so this is going to be sigma 1 squared over n1 plus sigma 2 squared over n2. So that part of it is not too bad. Now, how about the variance of that thing? And we've got independence, because these are two separate samples. So we can just add the variances, and they're going to be 2 sigma 1 to the 1 to the 4th over n1 minus 1 plus 2 sigma 2 to the 4th over n2 minus 1. Alright, so that's our pre-work that we did ahead of time. Now, what made this work when the variances were the same is that this thing inside the square root had a chi-square distribution. And we can say it has a chi-square distribution, and these are its degrees of freedom, and we're done. Therefore, the whole thing has a t distribution without degrees of freedom. In this case, we are not so lucky. If the two sigmas are not the same, over n2 does not have a chi-square distribution. My daughter has just come to grab some milk. This doesn't have a chi-square distribution. We don't know what distribution it has. And so this goes back to two chaps called Welch and Satterthwaite. And they independently worked out what to do. And they said, well, it's not going to be exactly chi-squared, but we can pretend it's approximately chi-squared. And that was what they did. That's my page 4. Let me see if I can... So not exactly chi-squared. But what we're going to do is we're going to pretend it's of the form, I'll call this W, equals A times a chi-squared with B degrees of freedom. We're going to pretend it's this. So if this is what it was, then the mean of W will be A times B, and the variance of W will be 2A squared times B. And what we're going to try and do is we're going to try and make this match up. We know the mean and the variance of this guy. And we're going to try and estimate A and B for this chi-square distribution so that these things match up as well as they can. So, let's see if we can do that. I'm going to need yet another new page. No, I'm not. Yes, I am. New page again. Alright. So, in other words, we are going to set AB, which is the mean, we'll set it equal to this mean. And we're going to set 2A squared B equal to the variance, which is that thing there. Alright, and then we're going to try and solve for A and B. Now, this thing here is not exactly chi-squared. We are pretending it's chi-squared for the sake of trying to make an approximation. It's going to be, we hope, fairly close to chi-squared. And if it were chi-squared, which it actually isn't, but if it were, then its mean would be this AB, and its variance would be 2A squared B, and we would try and estimate A and B. In particular, the one we care about is B, because that's going to be our degrees of freedom, our approximate degrees of freedom. Alright, now these are actually not as hard to solve as you might think. They're actually ugly rather than difficult, because if you divide the second one here by the first one, you get A. And so this is mostly writing. . and that's divided by the first one. And then the way you can get hold of B is to say, let's take the first one and divide it by A. And now I need a bit of space, so I've got to copy this. So I've got to take this one and I've got to divide it by, no, I've got to take the top one and I've got to divide it by B. So where I'm going to end up with is something a whole bunch of stuff squared. That squared divided by the thing that's on the top of A. Where are we? 2 sigma 2 to the 4th. And you can see how ugly this is becoming. This was back in the 50s. They had to be rather patient to work this out. So we pretend, and we are pretending, we have to bear that in mind, that this thing is chi-squared with that b degrees of freedom that we just worked out, this thing up here. And then if we can pretend that, then we are also pretending that T is approximately T to T distributed with b degrees of freedom, even though and sigma 2 squared are different. The last piece, which we need another page to say, alright, give me my mouse. New page at end. The last thing is to say, finally, in formula for B, estimate sigma I squared by the sample variance Si squared, because we don't know sigma I squared. And this is called the Welch or Welch STAC33, which is spelled like this. T. And it's for use when we don't assume equal variances. When we don't make that assumption. And so that says that even if you don't assume that sigma 1 squared and sigma 2 squared are the same, then you can still use a T distribution. It's just the T distribution has the degrees of freedom by a funky, ugly formula like this, like that formula for B, which may not even be a whole number. Now, I doesn't care about that. I can work with fractional degrees of freedom, and that's fine. If you are working with tables, you would have to round off. But the point is, this gives you some number of degrees of freedom which might not be an integer. And this is an approximation. It's actually a pretty good one most of the time. And it works even though we're not assuming sigma 1 squared and sigma 2 squared are the same. So this is a very general t-test that we can always use. And it turns out that even if sigma 1 squared and sigma 2 squared are the same, this Welch-STAC33 approximation is actually really good. So in practice, you might as well use this approximate t because you lose little. So let's write some of this down. You lose little by using this, even if those two variances are the same. And of course, you can never know for sure whether they're the same or whether they're not. But a lot of people, including R for that matter, will use this as a default. Unless you have a good reason for doing it differently, there's no reason to to go away from the Welch t-test, even though it's not the one you proved back in B27. That was the pooled t-test. So in other words, if you're willing to do all this work and get to this point here, if you're willing to do all of that with the sigma squareds replaced by s squareds, if you're willing to do all that work, or you're willing to let R do all that work for you, which is what it does, R has a function called t.test, and it defaults to the Welch, what it calls the Welch t-test. And I think they both deserve credit for the name, by the way. But it defaults to the Welch-Satterthwaite t-test because it's pretty good, even if sigma 1 squared and sigma 2 squared were the same. So that pooled t-test that you derived back in B57 is not really as useful as you thought it was. But in any case, this is how you can do a two-sample t-test.